pleasure to have Raymond Yeh give the talk in our colloquium today. Raymond, of course, was at TTIC as a research assistant professor for a year, 3 years ago. I'm pleased that you're having fun. So 3 years ago, and since then he has been faculty at Purdue, and he works on machine learning and computer vision, and his work is always very rigorous, which I like personally. Hopefully, this will be no exception. And he will tell us about immunizing models as opposed to people. Hopefully, that will not be outlawed. Immunization. All right, it's all yours.
Okay. Well, thanks for the introduction. It's great to be back. So today I'm going to talk about actually immunization and test time augmentation for pre-trained computer vision models. And this work, the topics covered in this talk is primarily done by my student Amber Chen and then Sean Yang. Okay, so before I jump into the details, I want to kind of have a high-level discussion on how I came to these two topics. And so this was a few years ago when we were looking at the state of computer vision research, or just computer vision in general. So the first observation that we have is that we rarely train from scratch anymore, right? The current kind of research paradigm is we have some foundation model or pre-trained model you can go and download, and then you start from there, right? Most computer vision models is built using the following strategy. Find a pre-trained model that has been trained on some larger data set, and then you go online, and there are open source models such as TIM, which is PyTorch image models. You go download that. Now you have the basis for it to start conducting your research. And then you fine-tune or adapt to the specific downstream tasks that you're interested in. And this is a strategy that has kind of driven a lot of research. And also, this is kind of the research strategy that graduate students are currently very comfortable with. I tried convincing some students to work train from scratch. None of them will really want to do that, unfortunately. And this is very different from several years ago. At least when I was a PhD, there's a trend in thinking about computer vision research as, we have these nice observations with nice handcrafted features, and you can just kind of replace them with learned features with a specialized architecture. Okay, so that's kind of where I was thinking about this. So kind of what does it mean for kind of my research kind of going forward, at least 1 or 2 years ago, right? So one possible direction is just think about, okay, since everyone's using pre-trained models, we should be just working on creating the best, largest pre-trained model and to get the most impact. Unfortunately, as an assistant professor, we somewhat need to be practical. Doing this will probably not be the most beneficial, and I will have a hard time convincing my students to work on this, unfortunately. So alternatively, right, I was given this advice by Greg, sitting a little bit, to hint me, it's like you should think further down the road, right? So specifically, I'm asking myself the question, okay, let someone else do this possible direction, and if you have the best pre-trained models, let's say in a couple of years, what would you be working on? So this leads to the two of the topics that I think is still relevant, even if we have the best large pre-trained models. So first is model immunization, where we try to mitigate the potential societal risk of having powerful pre-trained models. And second is test time methods that we can improve at test time the model performance once you're given these pre-trained models. So it's really conditioned on the fact that pre-trained models are here to stay. What should I do? And then these are the two topics that I will cover in this talk. Okay. So first off, model immunization will roughly cover kind of the content of two of my papers at ECCV 2024. Okay, let's get started. So the advancements in open source models, at least on the generative part, is there's like stable diffusion, deployed IF or Flux. So these generative models, are open source and makes it very easy for an average user to generate content, right? Content generation is just a few prompts away. Everyone can input some text prompt and get a reasonable looking image output. That had not been possible, just like maybe 5 or 6 years back. And these technologies truly beneficial, for the content creator and for everyone just to have fun or just to become an artist. However, this is what we learned from Spider-Man, right? With great powers comes great responsibility. With kind of advance in technological advances, there are also a risk of potential misuse. So I'm just giving some examples that was in the news last year, right? So this is George Collins. They sue over an AI-generated stand-up, especially that. I'm glad I'm dead, right? So it's probably not very respectful and maybe not even legal to do such a thing. And there are other exploit searches for Taylor Swift, right? Generate AI explicitly with fire, right? Probably not the best use case or the intended use case for people who are releasing these open source models, right? So the question that I ask is now, what should we do about it to mitigate some of these risks? Right. So there's a line of work, right? They try to remove harmful concepts from these open source pre-trained model. So it's called a model erasing or model unlearning. It works as follows. You're given a pre-trained model, data P, and then you're given some set of concepts of images and concept pairs that you want to erase from this model. Right? So you have your erasing algorithm, and it outputs a theta erased, where it can no longer generate these kinds of potential harmful concepts. However, at the same time, there's another branch of research that studies how do you efficiently personalize and adapt methods, adaptation methods. So this will be like Dream Booth or LoRa. So in this case, you can train efficiently with a few amount of training data, whatever concept that you want. So this is kind of like a chicken and egg problem in some sense, right? Once you remove it, I can apply these efficient and personalization adaptation methods to just relearn all these concepts back. So just unlearning is not enough to prevent bad actors when using a pre-trained open source model, right?
I'm a bit confused. Maybe it'll become clearer later, okay. So it's fine. But like, what are the concepts that I don't see the connection, I guess, between the unlearning and the risks that you mentioned, or what are the concepts that you want to unlearn here?
So for the unlearning,
what is the concept here, I guess?
I see. So for the set of concept, it's like kind of not safe for work content. So in pre-trained diffusion models, because they crawl the internet, it will already generate some kind of celebrity, and if you prompt it in a somewhat malicious way, it can actually generate kind of undesirable images that you don't.
So what is the concept that you're unlearning? I mean, I guess I don't exactly understand those.
Oh, I see. So here this.
But like, what's what's the concept? What do you mean by concept here, and what is the concept?
I see. So when I mean concept, it's really like you can think of it as a small data set where you have images and text pairs, right? So in this case, it will be like some artists. So for example, one potential misuse is you clone artists' work, right?
So that's misuse.
Yeah, so it's misuse, right? So by concept, it's just some pairs of data that's illustrative of potential misuse. So it's a somewhat broad kind of category that answers the question.
Because I'm still not sure what concept is.
So
maybe it'll become.
Let's give an example.
Later on, it's going to be more specific.
So it could be like.
I'm supposed to understand it from here.
I see.
Can we say that concept is whatever you want to unlearn?
Yes. So I'm using the term positive to be kind of whatever you want to unlearn, and whether it's unsafe or not, that's up to whoever decides.
No, but what do you mean whatever? What is it that is something that I want to? I still don't understand. What is it that I want to unlearn? Like when you say concept, is it like? This is not a categorization. This is like a part of the image space, a part of the word space, some specific thing. What is it here that you're? I mean, this is what I'm a bit.
So the space is both image and text paired, right? So let's say I don't want to generate a certain celebrity, I'll give it images of the celebrity and corresponding text pair of that particular celebrity, such that the pair together, which would, if you were to prompt it with, let's say, the celebrity's name, it will actually generate the celebrity's image. However, to unlearn it, you need pair data of both the image and the text. And that's what, together, I call that a concept. Kind of.
So it's the association between text and its visual depiction.
Yes. So we need that to unlearn the model.
Separate.
Yes.
That's because that's the nature of the model.
Yeah, that's part of the model, because it's text to the
In
image.
principle, if you just have pure noise to image model, then you don't need text. Just say,
That's
I want to
correct, yeah.
unlearn
So-
Van Gogh concept or something.
So I guess this is under the assumption that we're operating on these text-to-image generative models. So that's why it's a pair.
So you also achieved your. When I think of unlearning, I think of something that I could have just alternatively not included that in the training data.
That's
So
correct.
is this whole situation here? I mean, you would have been fine if you didn't include Taylor Swift in trail data at all.
That's correct.
But you made a mistake, you included her, and now you wanted to learn as if that data was not in the training data?
Yes,
Is
that's
that
correct.
Okay.
Yes. So unlearning is, you can think of it removing the particular paired training data from it. Right. But you did it after. You're doing it after the fact from a pre-trained model.
Okay.
Yes, that's correct. And then, right, I was backing. Then there's also research that you can efficiently train it back. Right. So that's why I say they're kind of like going against each other. So this means somehow we need a little bit more to prevent this from happening. So this is a line of work, right? How do you? What are some of the mitigation against adaptation? Right. So one of the ideas is you just somehow protect the data through data poisoning. So this actually one of the work is from Glaze, also from U Chicago as well. So the rough idea is like this. The adaptation method takes an image and a text pair and say they want to personalize, let's say, this guitar. You use your adaptation algorithm to output your specialized model, and then now it's capable of generating this specific instance of the guitar. Okay, so we want to prevent it from happening. So you put in kind of this defense mechanism where you modify the images with imperceivable changes. Yeah, imperceivable changes. Now this data is fed to this kind of data, same adaptation method as before, and now it no longer generates the desired guitar output. Right, so it's kind of used data poisoning to prevent the adaptation from learning the correct. I guess it's here. I will use the word concept again because in this case it's just a guitar and a text. Right. So this approach is effective, and one of the things that I want to point out is it puts kind of the responsibility for preventing these adaptation, or what I call malicious adaptation, on the content creator. Right. So before you want to release your content, you probably need to apply this data poisoning technique on top of it for this to be effective. So after seeing kind of this work, right?
Wait, sorry, I'm a bit confused here. You're poisoning the data that's actually used in the second phase.
Yes.
Okay. How do you have control? I mean, okay.
This is part work, so I mean,
Okay.
we can go into detail. but-
Okay.
Yes, yes.
This is Glaze.
Yeah, this is Glaze from
This is what?
No, this work from
Glaze.
Glaze from U Chicago. I didn't need to do this because we're at it, yeah. But the rough idea is you do data poisoning, and you modify the image such that this adaptation algorithm no longer works out. Okay, but so here we are presenting a kind of alternative way of thinking about this protection is, instead of protecting the data, there's the other component which you can touch, is you protect the model instead. Right, so this leads to what we call immunizing text-to-image model against malicious adaptation, which we named IMMA. Right, so the kind of difference from a data poisoning approach is that it takes the responsibility to do this protection is placed on the model releaser. Right, before you open source your model, you should run some algorithm to make sure somewhat you make it more difficult for the adaptation to happen. So it works as follows. Same as before, you have your adaptation, but now you take the pre-trained model, right? This is before you open source, you run it through the immunization method. It gives you a new model. If you were to apply your adaptation on top of it, and now no longer generates the kind of desired effect. Right? So you change the model instead of changing the data. So in the remaining, of this portion, I'll just describe how we actually achieve this. Okay, so basically, immunization is really formalized a bi-level optimization problem. So the idea is you use meta-learning to learn poor initialization for a given adaptation method. So you know which adaptation method is going to be applied and on which of the concept. And we just want to learn a poor initialization such that it's more difficult for these adaptations. So it's formulated with a upper level task where you want to maximize the loss function of the adapter. And then here, these are the model weights which you can change. Here, this phi here is kind of the parameters for the adapter. Right? And on the lower level task, you really just apply the adaptation algorithm and to find the best kind of adaptation parameters. So it's kind of, you're changing the model parameters such that the lower level task, which is your adaptation, becomes more difficult. And by difficulty here, we just measure it based on kind of the loss function, so we maximize it, where the lower level task tries to minimize it. So that's the high level idea. And the rest is just how do we exactly solve this bi-level optimization. So, yeah.
So this formulation does not talk about initialization. That just sets up the general goal of harming the best possible adapter.
Correct. So
okay.
We initialize it using the pre-trained model.
I know, but
Yes.
that does not involve. It doesn't yet talk about initialization specific. This subject, the formula.
Yeah, it doesn't, right? So
just to clarify.
the way we do it is we essentially use this objective, but we initialize from the pre-trained model, right?
So one way to immunize a model would be to completely destroy it. So is there some part of this that says you want maybe the small change, or that you want to still maintain some other functionality?
Yes. So we have some additional regularizor on top that says you cannot destroy the model, but details I didn't really put in here. Yes. So you also don't want to ruin the model entirely. But if you were to ruin the model entirely, it will actually just make the lower level test. Like you can't adapt on top of it. So that will also be a proper immunization, but it would just be a useless model to open source. Okay. So how do you then kind of solve this optimization problem to a degree? We follow basically gradient-based methods where you just unroll both the lower and upper level tasks into gradient descent loops, and you get this loop. And the subtle change that we did is we actually only optimized part of the model parameters. Is just the cross-attention layer. So there are actually more hyperparameter details to make this work, but that's in the paper.
So this is when you say you only modified that was what A does, or what you?
For data, yeah. So that's why this
This is
subscript
data,
S.
okay.
Yes. So we only changed part of the pre-trained model.
What I'm a bit confused, this is for a specific A, right? The A is the algorithm that your adversary will use.
Correct.
So you're assuming here that you have control, or you know what.
You know what A is. Yes. So you know A ahead of time, and you can allow to use it in the immunization. That's why this kind of makes it possible. And then we'll show a little bit of results on whether it's transferable across A. But yeah.
So I guess maybe it's premature, but if you have a small set of A's,
yeah.
Can you jointly solve it for that set at least?
Yes, in principle we can apply it. So you can have like multiple lower level tasks.
For example.
Yes. Yes. But that will make you have a loop over loop over loop, which we have not tried, but yes.
Raymond, I do not see any constraints here to control the quality of the generated output or the image. Does it?
That's what Avram was asking.
Yeah, that was yeah. So we do have additional regularization when we actually implement this, but because it's a little bit confusing to describe it all there. But I guess it's not. I should have included it in the description. Yes. So we have this additional to make sure you don't ruin the model entirely. Okay. So the rest is just experiment setup. So here, I'll specifically talk about immunization against a relearning of a specific artistic style and object categories. There are more settings in the paper, but the relearning algorithm, we consider we did LoRa and we did textual inversion and dream move. So these are the kind of very popular relearning algorithms. For evaluation metric, we introduced this term called a similarity gap ratio, SGR. So it roughly works like this. So, so you have your image generation of the model with IMMA applied, and the image generation of the model without IMMA. And then you have your actual reference image of that particular concept. So for example, it would be like, in the case for artists, you will have a reference image for that artist, this style. And then how do you evaluate? We have this additional image similarity metric M. So you can, it basically measures the quality of the generated image. So things like LPIPs, so minus LPIPs, we also did clip and dino embedding similarities. So the way to kind of think about this SDR is just, it's the performance gap that's caused by this immunization over the original performance. So it's kind of the ratio that we have. So let's look at an example and see. Right? So here I'm showing the reference image that we want to essentially clone the artist style of Picasso. And we apply LoRa. So on the x-axis, we're showing the number of epochs of the adaptation method. So as you can see, the 1 minus LPIPs, the higher means the more similar in human perception regarding to the input images. So on the x-axis, is as you train, you see the performance gets better. And if you were to initialize the model using a pre-trained model that has IMMA applied, and what you can see is that across the number of epochs, the performance actually does not improve that well, much. And you can see it's even going a little bit lower in terms of LPIPs. And here are the corresponding quality differences that you can see. And SDR really measures the gap at a fixed epoch between the model without IMMA and the one without IMMA. So that tells you the quality gap.
So here, the immunization was specifically for this adaptation task?
Yes. So specifically for this adaptation set, and it's only specifically for this particular concept. So we can only do one at a time. I'll talk more that we need to do that, but currently it applies one at a time. Okay. Yeah. And so we also have some qualitative results where we put these tables across, I think, across 8 different artistic styles. And the key thing is just SDR is all positive, so it means you're actually doing some effective immunization. And here are kind of the gaps between the epochs. Here we also showed results where you immunize against particular object generation. And as you can see for Gopal, actually towards the end, right, the more and more you train, at some point the training actually can kind of overcome the effect of your immunization. So this is somewhat to be expected, because if you think about it in the end, like, you can just completely retrain the model from scratch, and it doesn't really depend on the initialization anymore.
Here you keep the data the same, the amount of data for fine-tuning, for adaptation. It's fixed?
It's fixed.
Okay, so presumably you can't retrain the model on that fixed small
No, but in theory you could have a larger, if you have the access to the data. Yes.
But you can overcome the initialization issue.
Yes. Yes.
That's the only
Yes.
one possible use of computer just will run shorter training runs, but many of them, for example, and you will find. Okay, so you basically might not be preventing adaptation here, but making it
we're making it more difficult.
Expensive.
Correct. It's making it more difficult. That's why the term is called mitigating. We didn't say we completely protect it. So we try to make it more difficult, but we don't exactly completely prevent it. Right? That's not the claim of this one. Yeah. Okay, so let's look at more qualitative results. Right. So here we have this. These are the reference image, and if you use a erase model, it will just generate completely irrelevant images. However, you can apply relearning adaptation method, right? So without IMMA, you'll see that it's pretty much successfully relearned the style. However, with IMMA, it doesn't really learn the artistic style back. And this is also true for object categories as well. So here we have church, cassette player, and parachute, and with and without IMMA. So we do see some reasonable image quality that's still preserved, but it just generated something else. Yeah.
Do you have evaluation of how much the original generation capability will be lost after.
Yeah, so we do have that in the paper regarding the object categories. We have classification results. So how many percentage of the images can still be classified correctly? Don't know what's happening. Something is a little unstable. Yeah, so we do have that in the paper. Okay. And I think this is one of the questions that Greg was asking. Like, do you offer protection that generalizes across adaptation methods? And currently we have preliminary results that it's somewhat true, right? So you have dream booth and texture inversion. And if you were to apply with IMMA using dream booth versus IMMA with texture inversion, right? So the diagonal, obviously, this is what we presented so far. It kind of works. But the off diagonal, it also kind of works. But this is under some similarity in terms of the algorithm of dream booth and text inversion. So if you look at the adaptation algorithm, there's actually a large portion of overlap in the techniques. So the answer is yes, up to the adaptation algorithm is somewhat similar. So the question then that I want to go beyond is like, what is beyond IMMA? So first, one big limitation is that multiple concepts. Currently, we can only work with one concept at a time. And if you apply IMMA like sequentially, one concept after another, it will actually just completely ruin the model. So that's a problem. And then we hope to offer stronger protection and hopefully against more relearning algorithms, possibly unknown relearning algorithms. And then currently we have some other interest in working on other tasks such as few-shot classification or moving towards language, more general language and vision tasks such as visual reasoning. And yeah, so here I'll have a short summary of the first part of the talk. Right, so the key message that I want to get is like unlearned concepts can actually be relearned through adaptation methods. So even if we do really nice filtering or unlearning of undesirable concepts in the pre-trained model, it's not enough to prevent bad actors if we want to open source them. And we present a new paradigm to think about to protect the models against these malicious adaptations. And the kind of real new thing that we're offering here is a way to think about that it's not necessarily just the data's problem, but also the model's releaser's responsibility to do something about kind of what could be fine-tuned afterwards. And project and code, it's online. Yeah,
So just to kind of clarify now that you explained this work, its relationship to things like Glaze. So this is like specifically when you build a model, you kind of have to decide at some point before you release it what things you want to not allow, and then you immunize.
That's right. Yes.
Those. And that set is now fixed.
Yes.
So if some new danger comes along, you're out of luck.
Yes, so once I open source the model, there's not much, I don't have control
And
over
I think that in Glaze, the point is not that it's undesirable in a sense, like it's maybe desirable by someone, but you want to specifically protect, I think if I remember correctly, the whole point there is artists protecting their intellectual property.
So I think
this will not help with that because by definition, new art comes along after the model is released.
So I think it's not exactly the same, but my take on this is that both methods needs to be done.
Right.
So it offers a slight different kind of protection over, I guess, over Glaze, because that was specific focus on artists, right? So the use case, I think, I guess my point is that, to think about these, preventing these adaptation, something can be done towards the model, where, the priority is mostly focused on the data.
Yeah.
So that's kind of the gap I want to make.
So it's almost orthogonal.
Almost orthogonal, but the goal is somewhat
Sure.
towards the same, like we want to mitigate. Okay, so that's kind of the first part of the talk. And the second part of the talk, where I'll kind of pitch a question. Yeah, go ahead.
So, as you mentioned, like if you kind of fine tune the model long enough, eventually we do kind of learn the concept.
Yes.
So, do you have an idea that if you can completely make the model immune in the future, or you think it's like an intrinsic flaw of this kind of method?
Right. So you want to say like absolutely prevent it from happening. So I currently I don't want to make such claims because I don't personally think it's not possible. And we can talk offline. We're working on some more principal way of characterizing this on how to think about it. But in general, we're just making it more difficult to adapt. And it's really hard to get exact guarantees on whether it can be done. That's very difficult. And I don't think that can be done.
Do you know if the model still has internal representations of the concepts that have been unlearned and only the output is prevented, so that someone who is willing to dig into the internals of the model could pull out the knowledge?
So I guess the question is regarding whether it knows the concept, but it just will not output it, versus it actually really removed it from the model and prevented. So my guess is the first, right? There's some internal representation that's just in the opposite direction of the vector. So I think it's in there, it's just the model will not do it. So I'm sure someone will come along and say, okay, your adaptation can be undone as well and reverse your immunization. That I think will be possible.
I'm sorry, maybe I missed something. Isn't it necessarily that there's a representation? Because the model knows what it behaves differently. The model that was immunized versus one that wasn't immunized behaved differently when training the data. So it means
it has to know it.
Has to know
that's
it,
why.
right.
Yes. So I agree, right? You probably have to think about it's like you have a gradient in the opposite direction such that to prevent it.
I mean, the only way it wouldn't is if immunization was equivalent to removing it from the training set.
No, because it's no, but it's not.
It's not.
I mean, wait. Isn't the whole point?
No,
that's not
it's
what
not.
we
Yeah,
do?
it's not.
Yeah.
So, yes. So the model definitely knows. Yes, I agree.
That's different from unlearning.
It's different from unlearn. We're actually
And unlearning is about removing, and once you remove it, it really doesn't know.
Yeah. So we need to take this extra step to go in the other direction, which I assume someone can come along and be like, well, I just figured out the direction and flip it out. That can be done. But I also think that's still kind of like a form of entry of barrier, right? Not everyone is a machine learning expert and come along and just flip the. So it's debatable. I agree, yes. But this is a good thought experiment to discuss some other time. I'll put it that way. Okay, any question on this session? I'll move to the second topic on test-time augmentation. Okay. Okay, so I'll talk about test-time augmentation. So this is one we also presented at ECCB this year. So test-time augmentation is actually, just some background, is a very common way to enhance the model performance of a trained or pre-trained model, right? So the typical way is you take your data and then you generate variations of the particular input data. You run it through some deep model, and then you aggregate the output to make a specific prediction. So in this work, we're asking, are there other choices for the test time procedure besides just augmenting the input image? Can I do something to the model at test time that will still make the performance better? So the observation that we have is that existing trained architectures, at least for classification and segmentation models, often contains what's called pooling or subsampling layers. So here's an example in 1D. So if you're given a input 1D image X, and here's a 4-dimension, typically you have a subsampling, let's say by a factor of 2, and you just end up with all the even indices of that particular vector. And what happens to the odd indices is actually just discarded. So this is the typical set of downsampling or pooling layers. In the case for 2D, right, only a downsampling factor by 2 in both directions, you actually end up with essentially 4 pieces of this image, which the index S corresponds to the blue parts, and all the red, green, and yellow parts are discarded from the network. So every time a downsampling an input, information are thrown away. Okay. So in this work, we'll show that these discarded features, right, these are discarded at test time, is actually going to be useful for prediction, right? So you're throwing away information that's actually beneficial to make more accurate prediction. And then our method, right, which I'll describe, will actually work for CNN and VITs, and we demonstrate this to be beneficial on image classification and segmentation tests. Okay, so now I'm going to talk about how to do this. So just a slight background on image classifications to establish some notation. So image classification with DeepNet, you have your input image I, and then you have your output, which is y hat, given this image I. And typically, you can think of a DeepNet as a function of the classification, and also the feature extraction part. So the only difference between a standard DMAS and what the notation I wrote over here is that we have this additional vector S, which we call the selection vector, which really dictates, which of the downsampled component of the vector you're keeping. Right? So typically it defaults to 0. So your selection vector will be a vector of all 0, where you always select the 0, 0's kind of hash that you use for downsampling. Okay. So our approach for test time augmentation is we're going to essentially look through all the possible combination of the discarded kind of activation maps and say which of these are useful. And we're going to somehow merge them together into one single feature map to pass to the classifier to make an interpretation. So in order to do this, we need to essentially answer two questions. First is, how do we aggregate a set of feature maps? And second is, how do we know which of the feature maps that we should be aggregating over? So these are the two parts that we need to address. So let's first talk about aggregating over a set of features. So the goal of aggregated features, you're given a set of features, fs, with some set s hat that somehow we got somewhere, right? And we want to merge it into a single vector. So this aggregation function really is you can think of it as a function from RD to and the size of the set, and just merge it into RD. Right? D is the dimension of the feature map, and then you have the number of feature maps. And here I would roughly say that the number of feature map roughly correlates to the budget that you have. So think about at test time, you need to run 100 more times a feature map. That's going to cost you something, right? So I'm going to use the term budget, which really roughly correlates to the number of feature maps that you have. And here in this work, we present two approaches. First is a learning-free aggregation method, right? So you're given a set of feature maps, and how can we combine into one? So one form is just a simple weighted average, where you have one weight for each vector. And here, we propose to use the weight WS, which actually corresponds to the entropy of this final predictor from the classifier. So we have your entropy, and we essentially weight over, and we somewhat normalize it over the dimension. So the idea here is that you want to weight confidence, a feature map that generates confident predictions a little bit more. Okay. And then there's the second setting where TTA, so you can actually learn test time augmentation aggregation method. So there's a setting where you allow a small amount of training data to learn this aggregation function. So here we also propose a learnable aggregation method where we formulate essentially as a single self-attention layer. And the key insight here for W is that it's weighted based on the attention that's kind of computed between the similarity of these feature maps. So what is so kind of interesting in the way we're constructing these aggregation functions is that the two proposed aggregation are actually set operation. So why is this important? Because this means that because of set operation, it means that you can change the size of the set and its permutation equivariance. So you can permutation invariance. So you can shuffle your indices, and you will still get a particular shuffled output. And you can, and the module will still work if you have a larger size or smaller size set. Right. So what does that mean? It means we do not need to retrain this module if we decide to change the budget. Right. So let's say during my train time, I said I budget 10 feature maps, and I want to use 100. We can just use our model as is, as long as you give it a larger set to aggregate over. Okay. So some additional detail, we still also need to align the feature map before merging them together. So this avoids incorrectly averaging over different pixel locations. So remember that this selection index is really kind of like local shifts, or not local, sorry, global shift on the input. So what we need to do is just kind of resize it back to the original dimension, shift it, and then aggregate in the original original amount. So the feature map is actually pixel aligned. Okay. Then the remaining of the approach is just I just need to say, how do I find this set of useful features? So one idea is just you iterate over all possible selection index, but this is slow, and you don't want to iterate over it because this set grows exponentially as if the number of pooling layers. So instead, how do you tackle exponential things? One approach is just use some heuristic and put a greedy algorithm. And that's exactly what we did. So just briefly walk you through the example and not bug everyone with the algorithm. So we parameterize the kind of the selection index as a set of states. So let's say we have 3 downstream layers. And for each of these states, we're associated with criteria. So the lower, the kind of the better. Okay, so we start with 0, 0, 0. So you just run a for pass through a DNet and you get one criteria number for evaluation. And then what you do next is then, okay, you pick which of these layers you want to grow and explore additional extract additional feature maps. So in this case, we extract the first one. So we will check over different S index that shifts over at different feature maps. And then you compute this criterion. And you look at this again and say, okay, which one gives you the most promising criterion? And then you will grow this again. And in the end, you have a budget. Then you said, let's say the budget is, in this case, 6 feature maps. Then you just return these 6 feature maps.
So just to clarify, so each of these blocks involves, you choose a particular shift in layer 2.
Yes.
And then you train with that shift, or no? No.
You don't.
No, you don't. You just
You
do
don't.
it so you do it for in one image.
Yes.
Okay, so you just run the same trained features, but now looking at a different input at that layer, right?
Correct. Yes.
And then you look at the prediction. You are assuming that the task here is a multi-class classification, let's say.
It doesn't have to be, but yes.
Some classification,
Yes, some
you measure the
classification.
entropy of the predicted.
Yeah, so the criterion can be
class
entropy.
posteriors, and these numbers are that entropy in bits.
Yes.
Well, derived from the entropy in bits with your formula.
Yes. Roughly speaking. Yes. The criterion I haven't described out in the next slide. Depending on the.
Okay.
Yes. But yes. So how do we kind of choose the criterion to search for? Well, you use exactly how you aggregate those weights, right? So you want ones that aggregates a lot. Otherwise, you're just summing over things weighted with zeros, which doesn't give you much. So the learning free, right? Is basically as very consistent. Is based on the entropy of that particular index. And for the learnable one, you use the attention weights, right? So you really want to get the more meaningful example that's out of this weighted combination. So you want to grow, kind of greedily look for feature maps that has large contribution to that aggregation function. Yeah.
One thing that's a little confusing to me is you're still looking at very local operation, like pooling.
Yeah,
It's very local. But your attention could be, you can have weights at far away from patches or pixels that may not be local.
But the attention is over the selection index, so it's not the same, right? So it's
Or
attending
it's
over.
not over entire image.
Yeah, no, it's over that entire kind of between pairs of 2 different indices, and
I see.
then so it's not exactly the.
So it's still over those sets. It's not over the entire.
Yeah, it's over the set. The attention is over the set. Yes, so that's why it's WSS prime.
The set is exponential in size. So
Yeah, so that's why we grow greedily. Yeah.
it's a set explored so far.
Yeah, it's a set export. That's correct. Right. So it's kind of like a greedy approach to gradually grow until you reach your budget and you stop.
Just to make sure we're on the same page when you say exponential, so if you, let's say you have 5, like you have some traditional resonance.
Yeah, 5 layers. Yeah.
5 places where you reduce the resolution, and the stride is 2. That means you have 4 possible indices, right?
Yeah.
So it's 4 to the power of
That's
5,
correct.
2 to the power of 10,
That's
which
correct.
is not that big.
Depending on how many. Yeah, but you also don't want to run that at test time because remember this is
Right.
per input.
Okay, yes.
So that becomes expensive. Okay, so in terms of baselines, right, so we compare it to traditional test time augmentation, and then there's this work called AugTTA, which comparison is going to be made under the exact same budget, and then we just note that AugTTA needs to retrain a new aggregation module per budget, whereas ours just train on one setting and then just run. And here the comparison is mainly with just AugTTA. Okay, so here the TTA search space, right? So you can do augmentation and then with our approach, but under the same budget. So, right, because you can still do the standard data augmentation with additional to our approach, right? So this is kind of too orthogonal because you can still augment your image. And then here the budget is 30 feature maps, 100 and 150. Right? So this is on IMMA classification using Inception V3 model. And as you can see, the performance grows a little bit in the beginning and
So
gradually
the full
saturates.
set here is 1024.
Yes, if we want to do it over.
Yeah.
But then you also do across data augmentation. So it could potentially grow much bigger, like 5,000 or something. Yes. And then we also compare like the efficiency, let's say on ResNet with a fixed budget of 150. Right. So here we actually show that we can have actually a little bit more effective, lower compute than test augmentation. And this is because the way we extract the feature map and the shift indices, there are actually a lot of overlap, basically doing the standard convolution trick that we can share some of the compute. So that's why we can actually get more augmentation with less compute rather than just augmenting the input image. Additional results, we've applied to image segmentation. So how do we generalize a classification approach to an image classification, segmentation approach? You just treat segmentation as a per pixel classification. So the classics problem, and then you average over the pixels. And here's some results with budget 4, 8, just over this baseline. And here we show kind of the budget versus the accuracy on VIT. So just to be fair, right, so for VIT we see a gradual improvements every time we improve a little bit more budget. VIT improves, but this is not the case for Swing V2. And I think this has to do with how shift equivalent a pre-trained model is and related to this data augmentation method.
So if it were completely shift equivariant, it would kind of remove the need for this whole thing.
Yes. So this is kind of motivated by my previous work that because pre-trained models are not shift equivalent, what can we do? And this is one way to kind of mitigate that. Yes. So we will provide additional analysis. Like you could have additional heuristics that you have on the search space. So you can trade off between performance and inference times if you want to add additional ways of growing this search space. So you can decide to fix the first and the final search space and say I'm not going to search there. I'm just going to use the default 0. Or you can play with other combinations, and that allows you to trade off between performance and inference time. Other thing that I think is the most interesting is that in the end, we visualize the kind of the learn criterion and the entropy and the classification performance all into kind of one visualization. So each of this point here correspond to an individual feature maps of a particular of a set of examples. So what you see is that the learn criterion that we have actually somewhat correlates a little bit with the entropy, and then it also correlates like low entropy and like low learn criterion actually correlates with high accuracy. So this is really one of the reasons why this approach works. Is it allows you to select feature maps which kind of gives you high accuracy. But we're just checking this out.
What are the X and Y axes here?
So the y-axis here is the learn criterion. So we have this criterion that's used for searching. So here I'm just visualizing this entire search space and plotting those criteria on the y-axis. And on the x-axis, you can use the criterion to be like, let's say the entropy. So I'm plotting entropy on the x-axis.
So each dot corresponds to a set of indices. You select the layers.
Yes.
So again, assuming that you have 5 layers and 4 possibilities, you have 1024 dots.
But this is over a data set. Yeah.
Average.
No, it's not. It's just over.
Sorry.
Each
The
dot.
entropy is- Sorry, yeah, go ahead.
No. So what is one dot? I guess that's the question.
One dot is a feature map corresponding to a feature map indices S for one image.
Oh,
But you can have multiple images. That's what this is. This is visualized over a data set and over multiple S indices.
I see.
So that's why you also see groups of these. That's because every time you swap a, like if you have larger shifts, they cluster together. And yeah.
Wait, so this indicates that I'm still a bit confused, but this shows that entropy is a better criterion than your learn criteria, it seems.
But this,
Because it correlates better with accuracy.
but the accuracy is just per feature map accuracy, not the aggregated accuracy. So each individually, right?
I see.
Yeah.
So if you fix everything
I
else.
see, so this
and-
doesn't show us which one is better.
It doesn't show that. It just shows that it correlates that the learn criterion is somewhat a reasonable choice to entropy. And then we're showing that it correlates with accuracy. So the fact that more confident predictions actually gives you a little bit more accuracy. This is just, we're showing this on ImageNet. Yeah. So this.
Did you also look at images where this might hurt hurt the performance, and see if there is?
That's a good. We have not. Yeah. Maybe you should draw the same plot and look at which only plotted for the example that actually hurt the example, and maybe we'll see that
if there is anything.
It is on the other way. Okay. So just a quick summary, we show that some of the discarded activations are actually beneficial. So sometimes don't blindly trust the pre-trained architecture. There's something more you can do, and it's applicable to various testing settings and architecture and tasks. And the code is here. And before we go today, all right, there's always a bonus. I'd like to have a shameless self-promotion I'm doing here is to talk about all the other works from my group. I want to bring some attention. So I continue to work on equivariance and symmetry. So actually we have some works that are working on scale equivariance. So where you can kind of have a meaningful representation across scale. So if you take a regular CNN, extract some feature director, and downsample it, it's not going to be equivalent if you were to downsample first, then you pass it to C. However, we have a way that to actually ensure this to happen, and it shows some benefits of having scale equivariance. And regarding symmetry, I also have this very exciting work in collaboration with Rana on ambiguous generation. So this is just generating words that you can read after rotation. So this is word back, and if you were to rotate it, it still reads like word back. And here's another example for water. More. So these are just fun things. I can't make this into the talk, but I'll put it here. Other fun things, I've more recently to work on multi-object 3D grounding. So you take an image and a 3D point cloud of the scene. You want to ground the underlying, the referred 3D boxes that's mentioned in this text. And if you want to learn about other exciting words in my group, there's my website, raymond-yeh.com, and there is. Feel free to ask me any questions. I did this project just to have this for my slide.
Yes.
Okay. But yeah,
We do have time for questions.
Can I design an architecture that test time works without downsampling?
Test time works without downsampling.
Right, so I can naturally take advantage of whatever feature I compute from the image without losing the image.
But at training time, you still reduce the dimension to make it.
In case I want to make it efficient for training. But test time I can use full resolution. Every layer.
Yeah, that's something I've been thinking about. I have not seen works that done that. I guess it's related to somewhat like any resolution network, which is going in that spirit. But I've not seen it for classification tasks. But maybe it's just my lack of knowledge.
So if you're doing a true resolution, right? If you remember what that is, whole. Isn't that equivalent? The training time you can do it only for a subset of pixels, but at test time you just apply it everywhere.
Well, also classification at the end, you need to aggregate into a single number.
Because they're classifying the whole thing.
Right.
You can still do a global pool. So I think there's a difference between whether you can run it, right? You can design something that runs with a different resolution, but it will not be a very good prediction, right? So like a true conclusion, you can try with a rate of 8, right? You can run it, but the output will not be very good, right? So I guess it's still related to, maybe it's a little bit related to scale equivariance, a little bit, but there are more words that we can discuss offline on what to do there. Yeah.
Now that you brought up equivariance, want to know your opinion on, like many people believe that VITs are equivariant because there is nothing stopping it to not be equivariant, or at least for convolutions you have the zero padding which may creep into the network and you may have this, but for VIT there is nothing as such. But from the plot that you showed, the performance kept on increasing. So why do you think VITs are not that equivariant?
So there's a distinction in the equivariance literature, okay? Like typically the way we define equivariance is we want absolute equality, right? You have a properly defined a group, you apply this transformation on top of it, you get absolute equality. However, in the computer vision community, what people would say equivariant, they just mean loosely equivariant. It means it's similar. They don't have any guarantees, right? So I think that's the gap. Like, sure, convolution it's equivalent because you have a sliding window, but at the boundary it's not. So for most of the parts, it's equivalent. At the boundary, it's not. So I think that's the same feeling. It's whether people are using that term loosely or whether they're saying it's a precise definition of equivariance.
But in VIT you don't have. It's just simple patches, and you don't have any.
Patches are not shift equivariant because every time you do a patch window, you shift to another window. Now you lose your equivariance guarantee. So
But you have attention and grouping, so that should.
right, the equivariance is across permutation, not shifts. So the operation is different.
Is your VIT not using positional encoding?
But even after you use positional encoding, it's
No.
still not.
But if you're using positional encoding,
It
that
destroys.
ruins
It destroys.
any
Yeah.
sense of equivariance in which you would
Yes.
care.
So you can do relative positional encoding. So we have a work on how to make transformers truly shift equivariance where you can actually get equality guarantee. So if you're interested, you can feel free to check out our work on.
People in language have looked at that too.
Yeah, so you can do relative embedding to make it equivalent. So there are various other modifications that you can do to the transformer architecture to make it truly equivalent. So I guess that's one line of my work. You can read it. It says truly equivalent. It means actually I get that equality versus equivalence in general in the computer vision sense. So
I mean, I would
Fine
disagree with
distinction.
that. But it still can't be truly equivalent because the nature of images that you have, they are mostly centrally focused, and most of the patches that you look, even with self-attention, the corresponding patches that you are going to see, you will have a lot of similar patches around the center of the image as compared to the boundaries of the image.
The equivalence is a definition based on the function. So it's like your architecture. It has nothing to do with the data. So any data you feed in my architecture.